Welcome to the video lecture on differentials. Differentials are used to help approximate values to a function. A lot of times we'll have a complicated function or maybe even a function that we don't have a formula for. And what we're going to do is use a tangent line to help us approximate the value of the function close to some good point. So suppose that we have this curvy function here, this is our f, and we have some good point which I'm going to call c, so maybe right here at 2. If we look relatively close to C and we stay within that small window, you can see that the tangent line is a really good approximation to the actual curve itself. Now if we go far away from C, then the two start to separate and that tangent line is no longer a good approximation. But if we're close to C, then the y values on the tangent line itself are going to be very, very close to the y values on the function itself. And it's usually much easier to work with a nice linear function than it is to work with a more complicated curvy function. So this is going to be called a tangent line approximation. So how do we find this tangent line? Well, we know that we want to go through the point C for the x and f of c on the function. So that's going to be considered our good point, the one we know about. What we want to do to get our tangent line then is find the equation of the tangent line, which requires a slope. And the slope of a tangent line is just a derivative, the derivative at that good point C. So here would be the equation of our tangent line. Y minus the y value equals the slope times x minus the x value. And if we add this f of c over to the other side, then it just gives us this version or this form of the equation of our tangent line. Y equals f prime of c times x minus c plus f of c. And this is called our tangent line approximation. Now if we pick x's sufficiently close to c, then that should give us y values that can be used as approximations to the true value of the function. So that's what I was saying up here, where as long as we're close to c, the y values on the line should be really good approximations to the y values on the curve, which may be harder and more difficult to figure out. Okay? So for example, we want to approximate sine of 31 degrees using a tangent line. So what we're going to do is we're going to first figure out what our function is and what our good point is, and then we're going to find the equation of the tangent line through that good point. So what's the function that we're dealing with here? Obviously, it's the sine function, right? Sine of x. And the point that we're looking at specifically is 31 degrees, and that's not an angle that we're used to knowing about. We don't really know what the sine of 31 degrees is off the top of our head. But is there a good angle that's close to that that we do know about? Yes, 30 degrees, or pi over 6. And when you're doing anything in calculus, it's always recommended that you use radians as opposed to degrees. So I would prefer that you change that 30 degrees to pi over 6. So the good point that we're going to be looking at is an x value of pi over 6, or 30 degrees, and what would be the y value of the function at that good point? In other words, what is the sine of 30 degrees, or what is the sine of pi over 6? Well, that's just 1/2. Okay, you should know that from your unit circle. So this is going to be kind of our good point, our starting point. Okay, so now that we have our function and we have our point, we need a slope because we want to find the equation of the tangent line, which requires the slope of the tangent line. So how do you find the slope of a tangent line? You use a derivative. So the derivative of this function would be the derivative of sine of x is cosine of x. And what is the derivative at this good point, pi over 6? Well, cosine of pi over 6 is square root of 3 over 2. So now we have our point and we have our slope. This is going to be our m, and this is going to be our point that we use. So our tangent line will be y minus the y value 1/2 equals the slope, which is that square root of 3 over 2 times x minus the x value. And I'm going to use again that radian value, pi over 6, instead of the degrees because it works better for our derivative rules. So when I add this 1/2 over to the other side, we get y equals square root of 3 over 2 times x minus pi over 6 plus a half. Now you could certainly distribute if you want to, but I'm not going to bother right now. Now this equation right here is called your tangent line, but it's also called the linear approximation. Okay, so it is the line that best approximates this curve at the point pi over 6 comma 1/2. So that would be the best line that fits the curve. Now we want to stay close to pi over 6, otherwise that line is not going to fit the curve very well at all. So we want to make sure that whatever x we're plugging in, it's something close to this pi over 6. So what are we going to be looking at? What point are we interested in? We're interested in finding out what 31 degrees is. So what we're going to do is use 31 degrees in this equation. But because I used radians over here, I need to convert 31 degrees to its radian form as well. You want to be consistent with your units. So 31 degrees, doing a little conversion, there's 180 degrees in pi radians. So this is 31 pi over 180. So that's the x value that I am going to plug in to this linear approximation right here. So we're going to figure out what this tangent line would be at this point, 31 pi over 180. So let's plug it in. If I get a common denominator in the parentheses there, pi over 6, let me go ahead and erase this, would be, if I multiplied the top and the bottom by 30, this would be 30 pi over 180. 30 over 180 is 1/6. So all I did was get a common denominator there, and then 31 pi minus 30 pi is just pi. So this is going to be square root of 3 over 2 times pi over 180 plus 1/2. And if you punch that into your calculator, this is going to equal the decimal 0.5151. So what did we just find? What we found is that this decimal right here is approximately what sine of 31 degrees is. We didn't actually plug in 31 degrees into the sine function. We plugged 31 degrees into the tangent line. And since 31 degrees is close to our 30 degrees, we should be relatively close. And you could compare the two on your calculator to see how close they actually are. But the tangent line is a very good, simple way to approximate a curvy function. And it'll be fairly accurate as long as the x value that you're plugging in is close to the point where you centered your tangent line at. And we centered it at that pi over 6. Okay? Let's try another example. So here we want to approximate the square root of 4.2 using a tangent line again. So again, I don't know what square root of 4.2 is off the top of my head, but I do know the square root of 4. That would be a nice, good point that is easy to work with. So what we're going to do is we're going to let x be 4. So that means we're really looking at the point on this graph that's at 4 for the x, and square root of 4 would just be 2. So that's this point on my, whoops, I put it at the wrong dot. Sorry about that. It would be right here at 4, 2. So that's going to be my good point, the one that I know how to calculate very easily. What's the function that we're working with? Well, the complicated function is that square root curve. And trying to plug in numbers into that are not nice perfect squares is very difficult to do. So what we're going to do is we're going to figure out the tangent line at the point 4, 2. And we're going, at the point 4, yes, I said it right, at the point 4 for x and 2 for y, not 4.2, but 4 comma 2. And we're going to plug in to that tangent line 4.2 because that's pretty close to 4. So the y value at 4.2 should be pretty close to the y value on the tangent line. Okay, these two little dots are pretty close together. So how do we find the tangent line at this good point? Well, we need a slope, so we need a derivative. Square root of x is x to the 1/2. So if I bring down the 1/2 and subtract 1 from the power, this becomes 1 over 2 square root of x. And we want the derivative at this good point. So we want to know what f prime of 4 is. So if I plug in 4, that's 1 over 2 times 2, or 1/4. So my slope m is 1/4, and my coordinates of my good point are 4 comma 2. So my tangent line will be y minus this y value 2 equals our slope, which is 1/4, times x minus 4. And if I add that 2 over to the other side, then we get y equals 1/4 x minus 4 plus 2. And again, you can distribute if you like, that's up to you. So this again is going to be called our linear approximation to that square root function. It's much easier to deal with the equation of a line than it is to deal with a square root. So the actual square root of 4.2, I don't know what that is, but we're going to approximate it by plugging in 4.2 into this line. So I'm going to plug in 4.2 in for that x. 4.2 minus 4 is 0.2. So when we plug that into the calculator, we get 2.05. So the actual value of square root of 4.2 is close to approximately 2.05. That's what we just figured out. Okay, so now what we're going to do is take a look at some definitions and some notation. And it's a little bit confusing, I'll warn you in advance here, because we've got a lot of symbols and things that are all very similar but all a little bit different. So in this diagram, and it's a little bit faded, but what we have is this curve F, and then we have 2 points in black on that curve. So we've got C comma f of c. That's our good point. And then we have c plus delta x, comma f of c plus delta x. And that's the point that's a little trickier and harder to figure out that we want to know about. So first of all, delta x is this horizontal change between those two x values. So c being the good point and c plus delta x being the point that's slightly farther away. So delta x is that horizontal change. Now what we want to know about is how far apart are these y values, and that is called delta y. So delta y is the vertical distance from here to here between these two red dots. So it's this vertical distance right here. So delta y is defined to be that upper y value, so f of c plus delta x, minus f of c. So this y minus this y. Now what you can see, and it's a little faded again, but there is a tangent line going through that good point. And what we're going to do is, instead of actually computing this f of c plus delta x minus f of c and finding that actual second red dot, what we're going to do instead is use this tangent line instead to approximate the curve. And what we're going to do is plug in this point c plus delta x into our tangent line, which will be this point right here. Okay, so the actual change in y's can be approximated by this point on our tangent line minus this point on our tangent line. So this black vertical distance right here. and that is called the differential of y, and it is approximately the same as this f of c plus delta x minus f of c. And it has a formula, and it comes from just that slope times the change in the x. So the change in the y is approximately the slope times the change in the x. So this is called the differential of y, and it's called dy. Okay, we'll get to that in a moment. But the differential is the change in the points on the tangent line compared to delta y, which is the change in the points on the actual curve itself. Okay, so let's sort of talk through these definitions really quickly here. When the tangent line to the graph of f at the point c comma f of c, which has this equation right here, is used as an approximation of the graph of f, the quantity x minus c is called the change in x, and it's denoted by delta x. So that's this horizontal distance between these 2 points that we're looking at. When delta x is small, the change in y, called delta y, can be approximated by f of c plus delta x minus f of c. And instead of actually computing that, we're going to approximate it by using this part of our tangent line, the slope times the change in the x. And that's what x minus c is, just the change in these two x values. For such an approximation, the quantity delta x is denoted by dx and is called the differential of x. So delta x and dx will always be the same exact number for every one of these problems that we do today. The expression f prime of x dx is denoted by dy, and it is called the differential of y. So this is kind of a formula that you want to memorize, and it's basically just your derivative times dx. In many applications, the differential of y can be used as an approximation of the change in y. So the actual change in y, which is your delta y, is approximately your differential y when delta x is small. So the change in y will be approximately f prime of x dx. The true change in y would have been f of x plus delta x minus f of x. Okay? Delta x, or dx, is the horizontal change as you move from one point to another along a tangent line or along the curve. So up here in my picture, delta x is this horizontal distance, and that will be the same whether you're moving on the tangent line or on the curve itself. Delta y is the vertical change as you move from one point to another along the curve, whereas dy is the vertical change as you move from one point to another along the tangent line. So on my picture, delta y is the change from this red dot to this red dot. So that would be this vertical change in red, whereas dy is from this black dot to this black dot, and that would be this vertical change in those y's on the tangent line. And as long as your delta x is small, those should be relatively close to each other and good approximations. So here's our formulas. Your differential of y, called dy, is f prime of x dx. The actual change in y is called delta y, and that's f of x plus delta x minus f of x, and we can approximate that by using that differential f prime of x dx. The actual y value itself would just be the f of x plus delta x, and we can approximate that by taking the good value f of x and adding to that this differential f prime of x dx. And this is basically that equation of that tangent line where we're plugging in that good point into our tangent line. So let's practice. Again, this is kind of confusing with all this new vocabulary and terminology and different symbols. So let's start with something relatively simple, just finding a differential form. So don't let this confuse you, because all we're really doing in this next example is taking a derivative. If we want to find dy of the function y equals square root of x squared minus 4. Think about your derivatives for a moment. If I said find the derivative, we could call that y prime, we could call that f prime, and sometimes we call it dy over dx. So let's start with that notation here. Now to do that derivative, you would probably want to rewrite this as x squared minus 4 to the 1/2. And then you'd have to use your chain rule. You'd bring down your power, subtract 1 from the power, so the new power is -1/2. What's inside stays the same, and then you would multiply this by the derivative of what's inside, which is 2x. Now cleaning that up a little bit, the 1/2 and the 2 cancel, so I have that x, and then this is a negative exponent, so I can flip it down to the bottom, and a 1/2 is a square root, so let's change it. So dy over dx is x over square root of x squared minus 4. Now to turn this into its differential form, all you're going to do is split up this dy over dx by sort of cross multiplying that dx to the other side. So this becomes dy equals x over square root of x squared minus 4 times dx. And that's it. That's all we're doing. We're taking a derivative and we're just putting the dx on the other side. And that's called your differential form. Okay, so let's try it again with this one. Y equals x sine x. So let's start with finding dy dx. And in order to do this derivative, you need to use a product rule, because this is x times sine of x. So we're going to do the first function, which is x, times the derivative of the second, which is cosine, plus the second times the derivative of the first, which is 1. And that's just going to be x cosine x plus sine x. And now all I'm going to do is I'm going to wrap that in parentheses, and then I'm going to multiply this dx over to the other side. So this is now called my differential form. Okay? All right, now we've already done this problem once. We approximated sine of 31 degrees using a tangent line. Now we're going to do the same problem, but this time we're going to use a differential approach. So we're going to use differentials to approximate sine of 31 degrees. And they are very, very, very similar approaches. Okay? So this is the basic formula that we're going to be using when we do a differential approximation. This side is the actual value. So this is going to be that sine of 31 degrees. But what we're going to say is that it's approximately given by this side over here. This is your dy. This is your differential, and this is going to be the value of the function at the good point, the point that you could actually figure out in your head. So this is going to be like the value at the good point plus that little change along the tangent line to get you to the new point that you're looking for, 31 degrees. So before we start plugging things in, we need to figure out what's f, what's x, what's delta x, what's dx, all that good stuff. So let's start with our function. Obviously, the function that we're working with here is that sine of x. And the good value of x would be 30 degrees, because that's one we know how to evaluate in our heads, and 31 degrees is close to that. Now we want to use those radian measures again. So instead of using 30 degrees, I'm going to think of that as pi over 6. So dx, or delta x, remember those will always be the same, is how far away we are from 30 degrees. Well, we're 1 degree away. 31 degrees is 1 away from 30 degrees. So this would be 1 degree, but we want to use that radian measure again. So 1 degree is the same as pi radians over 180 degrees. Okay, just doing a conversion there. So delta x, or dx, is pi over 180. Now what we need in this formula, we also need to know f prime of x. So let's calculate that. F prime of x is the derivative of sine x, which is cosine x. So we have all the pieces. We're ready to start plugging in. So sine of 31 degrees is going to be the same as the function value at our easy or good point, which was that pi over 6, plus the derivative at our easy or good point times our differential dx, which is this pi over 180. It's how far away our good point was from our bad point. So what is f of pi over 6? Well, our function is sine, so sine of pi over 6 is 1/2. What's f prime of pi over 6? Well, f prime was cosine, so cosine of pi over 6 was root 3 over 2, and then this is going to be pi over 180. And I'm going to scroll way back to the beginning of our notes just so that you can see that that is exactly what we have right here. So we're going to get exactly the same decimal, 0.5151. The only difference is I put in this pi over 180 directly instead of putting in the bad value for x and subtracting the good value. We already computed that change off to the side. So that's the only difference between the tangent line approach and the differential approach. So this is going to be that 0.5151. So the actual value of sine of 31 degrees is approximately 0.5151. Okay, let's try this again for square root of 4.2. So again, the function that we're dealing with here is that square root function. The good point that would be easy to work with would be if we had square root of 4. So I'm going to let my x be 4, which means my delta x or my dx is 0.2 because the point we actually want to compute is 0.2 away from our good value of 4. We're going to need to know a derivative here, so let's compute it. This is x to the 1/2, so that's 1/2 x to the negative 1/2, or 1 over 2 square root of x. So the actual value, square root of 4.2, is approximately the good value at just 4 plus the derivative at 4 times this delta x or dx, which was our 0.2. So f of 4, our function was the square root function, so square root of 4 would be 2. F prime of 4 was 1 over 2 root x. So if I plug in 4 into that, square root of 4 is 2. 2 times 2 is 2, and it's 1 over that. So that's going to be 1/4. And again, if we scroll back to the beginning of our notes from earlier, that's exactly what this is right here. So we get 2.05. And the only difference is instead of writing x minus 4 and then plugging in 4.2, we just called that dx instead and plugged in 0.2 directly. It's the only difference between the tangent line approach and the differential approach. So this is going to be 2.05. Okay? All right, let's try some more. If y equals 1 minus x squared, find and compare delta y and dy with x equals 1 and delta x equals dx equal to negative 0.1. Sketch a graph and anticipate the results first. So our function, our curve, is y equals 1 minus x squared. So what does the graph of that look like? It's an x squared, so it's a parabola. It's pointing down because of the minus, and it's shifted up 1 because of the 1. So this is going to be a parabola that points down like this. And if you plug in 1 or negative 1 for x, this is going to be 0. So this has intercepts at 1 and negative 1. So what we're looking at is we're trying to find and compare delta y and dy when x is 1 and delta x or dx is negative 0.1. So the good point is this x equals 1 right here. We know that y value is 0 already. What we're trying to do is find out about another point that's negative 0.1 away. That's what this delta x represents. So negative 0.1 away would be at 0.9. So somewhere over here, and maybe this dot right here. So if I could find the actual change or difference in those two y coordinates, that's what delta y would be. What dy represents, if you visualize this tangent line, here's that point at 1, and then at point 9 we might be at this little dot on our line. So dy would be just slightly bigger than that, a little bit bigger change than the delta y would be in this particular graph. So we're going to find each of these and compare. So let's start with delta y. So the actual change in y, that's called delta y. And by definition, that's f of x plus delta x minus f of x. It's the difference in the two y values of your 2 points, the bad point and the good point. So here our bad point is at that 1 minus 0.1. The x is 1, the delta x is the negative 0.1. So that's just f of 0.9. The good point is f of 1. So we're just subtracting the bad point minus the good point. So if you punch into your calculator 0.9 into this actual function, you would get 0.19. And if we plug in 1 into the actual function, we just get 0. So the actual change is 0.19. Now let's compare that to our approximate change in y, and that's called dy. And the formula for dy is f prime of x dx. So we need to know what f prime of x is. So f prime of x is just the derivative of this parabola, which would be minus 2x. So we're going to substitute in 1 for x, because x is our good point, and dx was this negative 0.1. So negative 2 times 1 times negative 0.1 becomes positive 0.2. So if you compare these two results, you can see that they are very close. So the approximation using the differential ended up being a little bit bigger, just like we saw on our tangent line. This y value was a little higher than the red dot would have been. So that's why this change in y is a little bit bigger, but it's still close. It's still relatively close, so it would be a good approximation. Okay? Now the next example is pretty typical of things you would see in your homework in the textbook. So suppose you wanted to approximate the cube root of 7.9, and we're going to do it our two different ways, the differential approach and the tangent line approximation approach. So for the differential approach, what we're trying to do is we're basically using this formula. We want to find the actual value f of x plus delta x. This is the bad point. And we're going to approximate it by using the good point plus the derivative at the good point times that dx. So let's see if we can identify what's our f, what's our x, what's our delta x, and all that good stuff, and then we can plug it all in. So what function are we dealing with here? Hopefully that's easy to see. That would just be the cube root function, cube root of x. What's the good point? What would be easy to take the cube root of that's close to 7.9? Well, cube root of 8. Cube root of 8 is just 2. So let's let our good point x be 8, which means our delta x, or our dx, is what? How far away from 8 are we? Well, we're lower by 0.1, so this needs to be negative 0.1. Okay, now in order to use the differential approach, we need to know a derivative. So let's go ahead and compute that. F prime of x is going to be, this is like x to the 1/3. So if I bring down the 1/3 and I subtract 1 from the power, that becomes 1 over 3 times x to the 2/3. So I think we're ready to plug in f of the good value 8 plus that delta x, which was negative 0.1. So in other words, f of 7.9, or in other words, cube root of 7.9, that actual value is going to be approximated by f at the good value only plus the derivative at the good value times our dx, and our dx was this negative 0.1. So what is f of 8? Well, we go to our function, which is the cube root function. Cube root of 8 is 2, so this will just be 2. Now we need to know the derivative at 8, so I've got to plug in 8 up here. So this would be 1 over 3 times 8 to the 2/3. Now 8 to the 1/3 is cube root of 8, which is 2, but I have that square on there, and 2 squared is 4, 4 times 3 is 12. So this derivative is 1/12. And if I punch that into my calculator, we get 1.9916 repeating. So the cube root of 7.9 is approximately 1.9916 repeating. Okay, so that's the differential approach. It's basically just this formula right here. Okay, now let's contrast that with the tangent line approach. So the way the tangent line approach is basically you're finding the equation of the tangent line to the cube root function. So we're still using the cube root function, and we're still using this good point 8, but its y value, cube root of 8, would just be 2. So we want to know what is the tangent line to this curve at this point. And in order to do that, we need a derivative again, because that's the slope. So the derivative, we already computed that over here, was 1 over 3 x to the 2/3, and the derivative at our good point was that 1/12. So this is going to be my m, and this is my point, so we can find our tangent line by just doing y minus the y value 2 equals the slope 1/12 times x minus the x value 8. And if we add 2 to the other side, then our tangent line becomes y equals 1/12 x minus 8 in parentheses plus 2. So this is our linear approximation. Now what we do with this is, in order to find the cube root of 7.9, instead of plugging 7.9 into the cube root function, we're going to plug 7.9 into this linear function instead. So we're going to plug in 7.9 in for this x. So we're just using a nice linear function instead of a nasty cube root function. Now when we go to simplify this, look at what it turns into. 7.9 minus an 8 is a negative 0.1. So this calculation right here is exactly the same as this calculation right here. The only difference is that over here we plugged in that delta x or that dx directly, versus in the tangent line approach we actually plugged in 7.9 to figure out what that change in x is. That's the only difference. So these are the same, which means this final answer is going to be the same as well. 1.9916 repeating. Okay? Now let's see some applications about why differentials are useful and important. And this is something that you would see if you were a scientist doing experiments and possibly have some measurement error in your experiment. So here's a couple of vocabulary words here, if you will. Delta y, we know by definition, is f of x plus delta x minus f of x. Now f of x plus delta x is what we're going to call the exact value. F of x is that good value, which is our measured value. When we subtract these two, that's going to be what we call our propagated error. So the exact or the true value minus the measured value is your error that you incur during that measurement error. So here's an example. The measurement of the edge of a cube is found to be 12 inches with a possible error of 0.03 inches. Use differentials to approximate the maximum possible error in computing the volume of the cube. We're also going to find the actual propagated error and compare, and then we're going to see if the propagated error is large or small, and we're going to find the relative error, change in V over V. Okay, so there's a lot of stuff going on here. Let's first write down some of the things that we know. We know that we measured the edge of a cube to be 12 inches. So the measured value, And this is kind of like our good value, what we've been calling x, is 12 inches. The error when we measured it was 0.03 inches. So the measured error, that's going to be how far off we are from this good value. So the true actual measurement of the edge of the cube is plus or minus 0.03 from 12 inches. So either I could be as far off as adding 0.03 or subtracting 0.03 on either side of 12. So this is what our delta x or our dx is going to be, and it could be either plus or minus 0.03. We could have measured incorrectly in either direction. So that's our delta x. Our good x, our measured x, is the 12. Now what's our function here? We are trying to figure out the maximum possible error in computing the volume of the cube. So our cube here is, all sides equal, and I've been calling those sides x. So the volume of a cube is x cubed. So our function is just this x cubed. Okay? We know that when we're doing differentials, we need a derivative. So let's go ahead and compute that derivative while we're at it. This would just be 3x squared. And what we're going to call this, if our function is x cubed, that was our volume, then this f prime of x, we could call that dv. That's the differential of v. And if we put our dx on the other side, then that's that differential form. So dv is 3x squared dx. That's the differential form of the derivative of the volume function. So we have sort of the pieces in place. Let's go ahead and see if we can answer part A. So we want to approximate the maximum possible error in computing the volume. So the approximate error of the volume is exactly what dV is. Okay, that's your differential of V. Differentials are always the approximations. So what is dV? dV is the derivative of this volume function. So that was that 3x squared, and then to put it in differential form, we multiply that by our dx. So let's go ahead and plug in what we know. What is the x that we have? Well, that was our measured value, our 12 inches. And what is our dx? That's our error, our maximum possible error that we had, and that was either plus or minus 0.03. So if you multiply all of those together, then you get plus or minus 12.96. Now this is the error in the volume. So what would be units of volume here? If our sides were measured in inches, then volume would be inches cubed. So this means that our error, I guess I'll write maximum error in our volume measurement is at most off by 12.96 cubic inches in either the positive or the negative direction. So we're off by at most that much. That's what we just figured out, approximately. Okay? And that's just the approximation because that was using the differentials. So part B is to find the actual propagated error, and then we're going to compare the two. So approximate error is dV, actual error is delta V, the change in V. And that, by definition, is going to be our volume function at x plus delta x minus the volume function at just x. It's the difference in the good versus the bad points. So in this problem, our x is that 12, and then our delta x is either plus or minus 0.03. I'm just going to do the plus case because it's going to be the same whether you do plus or minus. And we are going to use 12 again over here for this x. So what would be the volume at 12.03 minus the volume at just 12? Remember, our volume function, since this was a cube, is just x cubed. So this is 12.03 cubed minus 12 cubed. And if you punch that into your calculator, that's 12.9924. And again, this is volumes that we're talking about, so the units would be inches cubed. So this is the actual error in measurement of volume. Okay? So how does this compare to what we had over here? They're very, very close. We got 12.96 when we did our approximation versus 12.99 for the actual. So they're relatively close, really, really close. So how do you compare how close they actually are? Well, that's called your relative error. You're going to basically convert it to a percentage to see how big or how little it actually is in comparison to the sides that you're measuring. So relative error for part C, by definition, is change in volume over volume. And what we're going to do, usually we don't know what this change in volume is. So typically we approximate it by the dV over V because that's easier to compute. And our dV in this case, remember from earlier here, was our 3x squared dx. It was just the derivative of that volume function with the dx on the side. So 3x squared dx over the volume function itself, which is x cubed. And when you reduce those x's, this just becomes 3 over x dx. And now if we plug in, our x was 12, and our dx was that plus or minus 0.03. So if you punch that into your calculator, that's plus or minus 0.0075. And we want to convert this to a decimal, and to convert any decimal, convert it to a percent. So to convert any decimal to a percent, you move that decimal 2 spots to the right. So this becomes 0.75 plus or minus 0.75%. So this is the percent error that we have, and that's less than 1%. So that means we have an error that's not too big. So this is okay. And if that's within your standards that you're allowing for measurement error, then you would be okay to continue on with your experiment. Okay? Let's try another example like this. Okay, in this next example, we want to use differentials to approximate the exterior volume of a spherical shell given that the thickness of the shell is 0.2 centimeters and the inside radius of the sphere is 100 centimeters. Also calculate the exact volume of the shell. So let's visualize here. We have this circle and we're making it into a sphere, 3 dimensions, and it has this slight, skinny little shell to it. And the thickness of that shell is 0.2 centimeters, and the inside radius from the center to the inside of that shell is going to be 100. Okay, so what we have going on here is a sphere that we want to know the volume of. Now 100 is a nice simple number, and we know that for volume of a sphere, hopefully you remember this formula. If not, you can look in the front cover of your book. But volume of a sphere is 4/3 pi r cubed. Now if I just wanted to plug in 100, that wouldn't be too hard to calculate. But because we have this thin shell here, our actual radius is not so nice. It's 100 plus that 0.2 extra little centimeters. So to actually calculate that real volume would require plugging in a radius of 100 plus 0.2. So the actual volume would be 4/3 pi times the full radius, which would be the 100 plus that 0.2, and then we'd have to cube that whole new radius. And you can punch that into your calculator and get 4213937.245. And since this is centimeters, this would be centimeters cubed. So that would be your actual volume, including the shell. Now what we're going to do is we're going to use differentials to approximate this actual volume. So the approximate volume Whenever you see that word approximate, you know that you're going to be using differentials, which means you're going to be using a derivative. This approximate volume is going to be based on the volume of the easy or good radius plus the derivative at that easy or good radius times the differential. Now in this particular problem, our good radius is that 100. So I'm going to be plugging that into our volume function, and I'm also going to need to plug it into my derivative. What's my dx? How far off am I really? Well, that's what this little shell thickness is. I'm really off by 0.2 centimeters. So we're going to use that 0.2 centimeters right here. So instead of plugging in a yucky decimal into our function, we're actually plugging in a nice number 100 into our function and only using that decimal over here in that dx part. Okay, so what is v of 100? Well, you'd have to plug in 4/3 pi times 100 cubed, just using a radius of 100. Then for the derivative, we need to know what v prime is. So to take the derivative of this, I would bring down the 3, and that's going to cancel out the 3 in the bottom. So we'll just get 4 pi r squared left over. So v prime of 100 would be 4 pi times 100 squared. So we're only plugging in nice values into our function instead of these decimals, 100.2. And then you can punch all of this into your calculator and get 4213922.946. So if you compare these, they are really, really close up into the tenths spot, okay, the tens position. So they're really, really close. So it would be, much simpler to just plug in that nice 100 and then use that differential 0.2 to help you get that slight change that you're going to be off by. So the approximation here using differentials is really, really close enough to use, and it's probably much easier to calculate if you have much more complicated functions. All right, let's try one more example talking about measurement error. The measurement of the circumference of a circle is found to be 56 centimeters. Approximate the percentage error in computing the area of the circle if the possible error in measuring the circumference is 1.2 centimeters. We're going to note that percentage or relative error is change in A over A, which can be approximated by dA over A. So what are we trying to do here? We're trying to approximate the percentage error. So what we just said in our note here is that change in A over in A, which is the actual percentage or relative error, can be approximated by dA over A. So let's see if we can figure out what this dA over A is going to be. Well, first of all, we need some formulas. We need a formula for this area, and we're talking about a circle. So what's the area of a circle? Pi r squared. So what would dA be? What would its differential be? Well, that's just a derivative. The derivative of pi r squared would be 2 pi r, and remember, in differential form, you put that dr on the side, since that's our other variable here. This is a function in terms of a and r. So the dA is on the left and the dr is on the right. So this becomes 2 pi r dr for the top, and the a on the bottom is that pi r squared. So if we reduce here, the pi's cancel and one of the r's cancels, so this is just 2 over r dr. So if I know what r is, I can plug it in, and if I know what dr is, I can plug it in. The problem is, I don't know either of those. They don't give me that information. What they tell me is that the measurement of the circumference of a circle is 56 centimeters. So they are telling me that the circumference is 56. Well, what's the formula for circumference? It's 2 pi r. And if you know that the circumference is 56, you can use that to solve for r. Just divide by 2 pi. So they didn't tell me directly, but there's enough information to figure out that our radius is 28 divided by pi. So now I can at least plug in that in for my pi. Or excuse me, for my r. Now we need to figure out what dr is. So dr is going to come from this last statement here. It says the possible error in measuring the circumference is 1.2 centimeters. Remember, possible error is that change in value, and we're talking about measurement of circumference. So the possible error in measuring the circumference is change in c, and we can approximate that by the differential of c, and they tell me that this change in c is this 1.2. So what we can do is figure out what dc is. Now remember, circumference is 2 pi r. So what would be the differential of this? To do that, you just take a derivative. The dc goes on the left side. The derivative of 2 pi r would just be a 2 pi, and then the dr goes on the right side. So dc is 2 pi dr. And we know that this is supposed to be that 1.2. So this is how we can solve for dr. Just divide by 2 pi. And now we know what to use for dr. So again, they didn't tell it to me directly, but they gave me enough information to be able to figure out that dr is 1.2 over 2 pi. So now if we substitute that in and try to simplify here, we are going to have 2, and I'm going to go ahead and multiply by the reciprocal of 28 over pi. So this becomes pi over 28, and that's being multiplied by that 1.2 over 2 pi. So the pi's cancel, the 2's cancel, and 1.2 divided by 28 is 0.0428. Now when you do these change in a's over a's or anything like this, this is percentage error. So the answer we get here isn't a percent yet, it's just a decimal. To turn it into a percent, you want to move that decimal 2 spots to the right. So this is 4.28% error. So this is our relative error. And again, it's not too big because it's, less than 5%, so it's fairly small. So the approximate percentage error in computing this area is still relatively small. Okay? All right, our last examples here are pretty similar. Here we have the function square root of x, and we want in part A to give a linear approximation to this function at x equals 9. So whenever a question is asking you for a linear approximation, the best line that is always going to fit your curve will always be the tangent line. So a linear approximation just means find the tangent line. And we're trying to find the tangent line to this function, square root of x, at what point? Well, we want to find it when x is 9. Well, what would be the y coordinate if x is 9? Well, since our function is square root of x, square root of 9 is 3. So this would be 9 comma 3. And you can't find a tangent line unless you have a slope, and a slope is a derivative. So let's go ahead and find our derivative. Square root of x is like x to the 1/2. So I bring down the 1/2, I subtract 1 from the power, and rewriting this, this is 1 over 2 square root of x. We want the derivative at this particular point. So let's plug in 9. So that's 1 over 2 square root of 9, which is 1 over 2 times 3, or 1/6. So now we know our m, and we know our point. So we put them together, and our tangent line is going to be y minus 3 equals our slope, which is 1/6, times x minus the x value 9. And if I go ahead and I add my 3 over to the other side, we get y equals 1/6 x minus 9 plus 3. And this is called our linear approximation. This will be the best fitting line to the square root curve at the point x equals 9. So now what we're going to do is we're going to approximate f of 8.9. So we really want to know what the square root of 8.9 is. But figuring that out would be difficult to do because it's a yucky decimal being plugged into a yucky function. So what we do instead is we plug 8.9 into our line instead, because plugging it into a linear function is easy. So this is approximately 1/6 of 8.9 minus 9 plus 3. Using a linear function is much easier to compute. This will just be 1/6 of negative 0.1 plus 3, and as a decimal, that just becomes 2.983 repeating. Okay? So square root of 8.9 is approximately 2.983 repeating. And it should be a pretty good approximation because these 2 points weren't too far apart from each other. Okay, then for part C, find the differential dy for x equals 9 and delta x equals negative 0.1. Now this is just a formula. Your differential is always your derivative times dx. And we already know what our derivative is. It's right here. It's 1 over 2 square root of x dx. So all we have to do is plug in 9 for the x and plug in negative 0.1 for dx because delta x and dx are always the same thing. So this is that 1/6 times negative 0.1, and as a decimal, that's negative 0.016 repeating. Okay, so that's approximately how far off our approximation is from the true value. Okay? All right, our last question, very, very similar to the last one, but the big difference is we don't actually know what our function is this time. We don't know that our function is a square root function. All we're told is that f of 2 is equal to 6 and f prime of 2 is equal to negative 1. And this is actually more realistic because when you're doing real life experiments, you're really just collecting a bunch of data and you don't actually have a function or a curve that you know the formula of. You just have a bunch of data points. So it's possible that you could collect some data and figure out that at one point the function is going from 2 to 6, and then you could find out that its rate of change at 2 is negative 1. That's very realistic that you might know that information, but you don't actually have a formula for this function. So one easy way to approximate this function that we don't know of is to find its linear approximation. And remember that a linear approximation will always be best when it's the tangent line. So all we have to do is find the tangent line to this function, which means we need a point and we need a slope. Well, what point are we going through? We know that x is 2. What's the y value of this point? Well, we know that because we know that f of 2 is 6. So 6 is the y coordinate. Now, for a tangent line, we also need a slope m. Do we know that? Do we know a derivative? We do, because the derivative at 2, they tell me, is negative 1. So we know a point, we know a slope, we're ready to write our tangent line. So our tangent line is going to be y minus the y value 6 equals the slope, which is negative 1, times x minus the x value 2. And I can go ahead, these numbers are easy enough that I can just go ahead and distribute that negative across and then add 6, so we get y equals negative x plus 8. So here is a linear approximation to our function f that we don't know what it is, but here's a linear approximation to it. So what if we really needed to know what our function was doing at 2.1? Since there's no formula for f, we can't exactly plug in 2.1. So what we do instead is we use this very simple linear approximation and plug in 2.1 into that. And that's what modeling is all about. So all we're going to do is say that f of 2.1 should approximately be 2.1 with a minus in front. Let me write it a little bit more clearly here. We want negative x, so negative 2.1 plus 8. I'm just plugging in 2.1 in for this x. And that is going to give you 5.9. So approximately this function at 2.1 is about 5.9. Okay, and then finally here, the differential dy, there's that formula again. dy is f prime of x times dx. So the x that we want to use is 2, and our dx is the same as delta x, so that's this 0.1, since 2.1 was 0.1 away from 2. And what was f prime of 2? That was this -1. They told me that. That was a measured value. So -1 times 0.1 is just going to be -0.1. So there's our differential. All right, that concludes our video lecture on differentials. Good luck.